something?
Yes, counter just went down to takeoff. We're live and recording.
So, okay, it says so. Okay, good. So welcome everybody. I'm really sorry for the delay. I forgot there was a World Cup. I had like guests, all this stuff, football and all this. Was hard, a bit of distraction. Yeah.
There's
so
a bit of...
and also I was struggling with the slides. Yeah.
Oh,
yes,
Dimitri has a bit of a hectic day, but will hang on as long as he can.
Yeah. That's one of the things that I'll try to get over as soon as possible.
Claudia
maybe
Baron say hi.
Yeah. Okay, on that, because not many people, the regulars attending the live session, some of you might be leaving before. Maybe George, you can ask on the chat whether part B, if the majority prefer us to have the part B on Sunday or something, or maybe next week.
Okay, yeah, I don't know how to do that.
While people are thinking, I can just I guess we can just ask on the thing, whoever, see if you have any consensus.
I'm just typing the question in on the chat.
Okay.
When do people prefer part B, on Sunday or next Friday? And for those of you in YouTube land, you can also put your opinion down in the Discord.
I'll be mostly biased towards the ones, the regulars attending right now. Yeah. If whatever the majority, I will probably, because the ones on YouTube, I'm sure will not mind. Yes.
So I'll just repeat. Okay, and we're getting some feedback. Baron and Dimitri like Sunday.
Okay.
And they're both regulars.
Okay. Anyone else? And at the same time, I guess I'm happy to do early as well, if that's more convenient for most people, because I know Sundays people have a commitment and all this.
Sorry if I wasn't clear. Yes, that's this coming Sunday.
Okay.
Okay.
While we wait for the, go ahead.
Oh, sorry. Yeah, there seems to be a time delay, Crosstalk. This Sunday works for Dimitri as well.
Okay.
I'm trying to remember. I think on Discord, Amir said Sunday would work for him, except it would be earlier in the morning for him, which would 3 hours earlier. And so, oh God, I can't do this in my head anymore. My math is going.
So anyway, I think it's 9 o'clock is time. Yeah.
Yeah.
Go ahead.
It's on the Discord.
Okay. I'll
right,
check
9 o'clock. So that would be 4 hours earlier than the usual time. Oh no.
Yeah.
No, wait a minute. That would be the usual time. No.
The usual old time.
Yeah.
I think.
Right, it would be noon for me, so the old time for you.
So. Yeah. Which is fine for me.
So we can put that as an alternative as well on the Discord. I think we should, giving preference to people who are the regulars, have the final tally on Discord. Because some YouTube viewers might be able to attend at different times that aren't regulars.
Yeah, yeah, yeah. As I said, I will be biased towards those who attend the session live. So yeah, just to make it more interactive. Yeah, so I'll come back to the polls after the session. So because I know some of you, like Dimitri, might be in a thing with the time. So not at least Argentina is playing, I believe. Some people might want to, yeah. Yeah, so welcome to session 20A. So there will be a session 20B, and that will be it for this crash course on group theory. And then the next course will be the Lie groups and representation. And today's session is actually to give you a little bit flavor. Today and the next session will be to give you a little bit of a flavor about representation theory. So when you go to the next course, you are not like, being hammered with something that you never heard of, or you are not feeling that comfortable with. So yeah, so we'll just scratch off the surface of the representation theory that we'll touch. But hopefully that will be enough to give you some sort of a sense about, how the idea, the basic idea behind representation theory, and some examples. We will be mostly working in the abstract, just to give you that, to force you to feel a little bit more comfortable with the things. There will be some examples, but mostly we'll be working mostly on abstract. And the good news is the abstraction, for those of you who have been following the thing, will probably not be that hard for you. Yeah. So, okay. So just in a nutshell, the idea behind group representation is really this way of getting an abstract group and representing its elements as matrices, right? So why would you want to do that? A good example is, for example, in the crash course. I know, George, you can comment on this. When you have like a permutation groups, for example, I know some of you have like a lot of hassle, trying to, do the computing, the product of two cycles and so on. So matrices are much more less abstract to perform computation with, less hassle, I would say. I don't know if you agree, George.
For me, I know some people think more combinatorially and algebraically than I do.
Yeah, so the idea of group representation is really, in a nutshell, this idea of getting an abstract group. You can work your theory in abstract, but then if you want to do computation about something, you don't represent the group elements into something that you can do computation with much less hassle. So this is really in a nutshell. Okay, so the first abstract definition is this. So given a group, okay, this can be any group, it doesn't matter what type of group, it can be, a finite group, an infinite group, a matrix group, or whatnot. We say an n-dimensional linear representation of the group G is a pair, okay? It's a pair made of this thing, made of an object we call V, and another object we call, how do you read this in Greek? Is it rho?
Yes.
Yeah, so it's a pair, but not just any pair, it's a pair that satisfies this. So the V is an n-dimensional vector space over a field, okay? In our case, we will specialize only in the complex, in the field of complex numbers, but this could be any field of any characteristic, okay? And the rho is a group homomorphism. So it's a homomorphism from the group to the general linear group of the n-dimensional vector space, okay? So just as I was saying, for practical purposes, in our case, we will just focus on, on the field of complex numbers, but there's nothing special about this. It could be R, but it's just for our purposes because, we want to get to unitary representation, and these things that are, more relevant to quantum stuff. Okay. Now, in the last session, I believe, or the session before, we have seen that GL of V is actually isomorphic to this, to the general linear group over the set, the group of invertible n by n matrices. Okay, so that means we can actually think about this homomorphism of the representation as a homomorphism from the group to this to the set of n by n invertible matrices. Okay, so the trick of representation here is really to go from abstract sometimes to the thing, to actual concrete realization of the thing, of this set here. So we will follow that. Sometimes we will work with GL of V, but sometimes it's convenient to just go to use this one, to the invertible, the group of the invertible matrices. It's much more easier, concrete. Another thing is, you can obviously, given the homomorphism from the representation, you can construct a left action, right, acting like this. So you take a pair, you have the group element, you have the vector in the thing, and then you just, because this guy, rho of G, is a linear map. So therefore, you can, obviously act it. If you act it to the left, you get another vector in V. Okay. So this is why, remember, when we are talking about group actions, group actions are actually homomorphisms from the group to the group of the symmetries of a set as we define it abstractly when we talk about group actions on a set, for instance. Okay. In our case here, we are talking about group action on something that more than a set, on a linear structure, on a vector space V, but it's the same thing. It's similar thinking behind it. And another definition is faithful if it's injective. Okay, so that means that if we have rho of G1 equals rho of G2 if and only if.
Bambode, your sound is cutting in and out.
Equals G2. Okay, so this all is a faithful.
Bambode, can you hear me?
Do we have anything on the chat? Because I cannot see.
No, I was just trying to let you know that your sound is cutting out. I wasn't sure if it's an audio problem or a network problem.
Okay, with me?
Yes. I don't know if my sound is okay for everybody or for you.
Yeah, what about the rest? Your sound is okay to me. I'm just, the rest, if I missed anything. And I hope there won't be any typos, but I guarantee there will be a typo somewhere.
Now we do have a comment from Barend wondering if there's an example of rho of G1 unequal to rho of G2 if G1 equals G2.
I don't quite understand, because if there is an example of...
I'm trying to read this. Rho of G1 unequal to rho of G2 if and only if G1 equals G2. Is that maybe a question of whether it's surjective as well as injective?
Yeah, this is saying only if it's injective. This is only using injectiveness to define this.
So in other language, 1-to-1, which is maybe more for the analysts.
Yeah. It's easier to see it that way.
Barron's.
Because remember, this row, this might be going to a subgroup of GL of V, not necessarily to the entire GL of V.
Yeah, not all homomorphisms, or not in general, not all functions are 1-to-1. Some functions will map. Oh my gosh, maybe I'm muddling this. Maybe Bamborde can explain it better.
Yeah. So remember, this is a map. It goes from G to GL of V. It doesn't necessarily hit the entire GL of V. This could be the image. So the way to say this, actually, formally, I would have written is going to the image of this, which is a subset of GL of V. It could be the entire GL of V. It could be just as, it hits, just a corner of GL of V. Okay. You'll see some examples in a minute for you to be able. Yes. There are some exercises. Yeah.
So Amir is asking, does that imply that it's bijective?
When you say bijective, you will say like the entire thing here is being mapped to the thing here. Yeah.
The image would be the whole space.
Yeah. The whole space. Yeah.
The main thing I get out of it is that in this context, faithful is synonymous with injective 1-to-1.
Yeah. So you can, I guess this is where mathematicians are a very good thing at naming stuff. If you confuse, just think about marriages, being faithful, not cheating, a couple. So you have like a couple, so they are like, 1-to-1. There's no like one of the couples having being hit by another person. Okay. So this is a way to view this, I guess, in a natural. That's why they call it faithful.
Yeah, there is two ways a function can fail to be a bijection. It can fail to be surjective, covering the whole of the target, and it can fail to be 1-to-1.
Yeah. So in our case, we are saying 1-to-1. Yeah. Okay, you'll see some examples anyway. The good examples of this actually. To see where the thing goes from one group, but actually we are actually narrowing our thing in the subgroup of the. You'll see in a minute. Okay. So one thing I want to call your attention to is in a lot of textbooks, especially those that are tailored to physics, actually people don't use the row. They use like pi, which is a bit for me a bit confusing because sometimes you can mistake it with other notations where pi pi means something else. So yeah, that's why in the abstract I'm using this. Yeah, go ahead.
In a bad font, a bad PDF or book, it can be hard to make out. Greek rho looks very like italic English P.
Yeah. Yeah. So this is a notation thing, but it is the same thing, just insert. There's nothing. The thing, if you see this on whatever textbook you pick, it's just the convention that the person they use, pi. I decided, and other people they also use like rho. Okay. I like to do this because this is a thing in the abstract, so we are not like, another thing is, this is also a source of confusion sometimes, especially for newbies, is, as I said, a representation, as we've seen, a representation is a pair, Okay, it's something that you construct. You pick a vector space and you pick a homomorphism between the group and the general linear group of the vector space. Okay, but in some textbooks they refer the homomorphism as if it's just this. So they would just write, let's rho be a representation. By that, that's mostly like done when V, the vector space V, is understood from the context. So you don't need to mention the vector space. But very often, actually, even when people are working in abstract, a lot of authors still just references the homomorphism, so they ignore the vector space. Okay, so it's pretty much like we were doing with topology. We have the topology, and then we have the underlying set. But we say X is the topological space, but actually the topological space is actually the set X together with the topology on X. So it's similar thinking here, just for you to be aware. Okay, so here's an example. Okay, so we are talking about a concrete example. So the first one is, let G be any group. Okay, so we can construct an n-dimensional representation like this. So we define P of G. Sorry, P. See, I'm calling it P. We define rho of G to be equals the identity for all the group elements in G. So the claim is this is a representation because this is a homomorphism. You can verify this. It's a trivial one, but it is. Okay. So now let's see a non-trivial simple example with finite groups. Consider the permutation group, this one, which is a subgroup of S3. I hope I didn't make any mistake. I think Bob is very good with permutation groups. So Bob, the eagle eye. Yeah, this is I claim anyway, this is a subgroup. And then I claim we can construct a three-dimensional representation as this. So we map the identity permutation to this, and then we map this other cycle to this matrix, and this one to this. And the question I ask, based on the definition, is this faithful? Especially for the ones that were confused about the definition of the faithfulness and all this. Do we have any answers on the chat? This is easy to see, right?
The way I see it, the way I see it is that you're permuting the columns according to the abstract permutation. So you're going through the cycle. You're moving the columns around. Yeah,
there is actually we will do that in the next session. That's one of the reasons I wanted to split this in two, because it's a bit of hassle to do. Is to do the standard representation of Fn.
Yeah.
Of the permutation group Fn into GL of NC.
I mean,
so that will take us to that will take you along the line of what you are saying. Yes.
What I mean is, from this picture, you can see that it's faithful in that all of the columns are there in each of those matrices in the middle and on the right. If you look at them, all of the columns are there, so you can visually see that it's faithful.
So everyone agrees it's faithful? Can you all see? You don't need to see it the same way as George, but is there the most important thing is that you came to the same conclusion, right?
I have Dimitri on my side in the chat.
Okay. What about the rest? We're asking about faithfulness. Berend and Amir, what do you think? Do we have a consensus? Yes?
I guess silence is consensus. Speak now if you disagree.
Excellent. Yeah. So I'm writing here complex representation, just a reminder that we'll focus on the thing on the on complex vector spaces. Okay.
Oh boy, I wasn't even thinking of that. I was just thinking of the finite field of zeros and ones. My bad.
Okay. So here's a challenge. So let's G be the entire group S3. So the challenge is for you to construct a faithful three-dimensional representation of G and try to construct a non-faithful three-dimensional representation. Oh, there is a typo here. I knew there was. So there's a faithful repeating twice. So there you go. Yeah. So this is the first challenge. So the second line is a non-faithful three-dimensional representation of G. That's also I forgot to add, but I guess you understand what I mean, right? Because I got this one right without typo. I'll correct the slide before.
Yeah, I think that's
yeah.
Working through that might help to understand faithful and one-to-one.
Yeah. And whether you do it before on Sunday or something, or before or after, depending on what people prefer, you have to take your time to. What I will do actually, in part B, I will use the same slides, so you don't have I won't produce two separate slides. So I will continue from these slides to make it easier. So everything is in one.
Dimitri is commenting that we actually just saw the faithful in this previous slide.
Yeah. So what I'm asking is another one. Yeah. And this is actually a very good point Dimitri makes, because then if you say, well, if we find another faithful representation, how can we use, this is just using the colloquial term, we'll have a formal definition of this. Are they equivalent? So the notion of two representations being equivalent, we'll come to that in the next few slides. Okay, so when you have any structure, you talk about substructures as well, right? And the way to induce them as well. But this is not the case. We'll talk about subrepresentations in few slides. This is actually about using the parent group in order to generate another representation from a subgroup of it. Okay, so let G be a group and H be a subgroup of G. Okay, so if this is a representation of G, then the claim is V together with the restriction of rho to H is a representation of H as well. Okay, where this restriction, just as a refresher, remember, when we talk about restriction, we mean you ignore, you just consider this map to go from the subgroup to actually there's a typo. I'll ask you if actually to see if people can see this. Do you see a typo here? Is it a typo or is it not a typo?
I guess rho restricted to H is a different representation.
Is there a typo, or is it just I'm throwing a confusion to see?
It's. I don't see a typo in proposition 1. We need an eagle-eyed Bob for the typos.
Okay. What about Dimitri?
Let me see the chat. Quiet in the chat.
Okay.
Let me scroll down. I think proposition 1.0 is no typo. It looks good to me.
Okay.
I read further down, yeah.
Everyone agree? Remember, this is okay. Of course, this is a restriction. It goes from H to GL of V. So it's a homomorphism, right?
Yeah.
So therefore, it's a representation as well. So this is a representation. So yeah, I was just throwing that to see if people get a bit thrown off to try to think, have any doubts. Yeah.
Yes. So okay. Now we have agreement, no typo. I think it's very trivial to show that the restriction also preserves faithfulness. That's really just the challenge.
Yeah. So this is a way. This is actually telling you a way of when you have the bigger group to construct when you want to construct another representation. You can use the bigger group. You can if you have a representation of the bigger group, then if you want to build a representation on the subgroups, you can just use the restriction on the thing on the restriction map on that subgroup, and then there you go. You have a representation. It might not be an interesting representation, but nevertheless, it's a representation.
Yeah, maybe it's not clear that the notation rho restricted to H is actually a mapping as well, just a subset mapping.
Yeah. That's why I put here where, this yeah. What about this one? So let's G1 and G2 be groups and phi be a homomorphism from G1 to G2. Okay, so let's assume this is a representation of G1. The claim is I hope I didn't make any typo. Again, this is a good thing. The claim is the composition, this V together with this composition is a representation of G2. In other words, this is another way to say this is that this composition is a homomorphism from G2 to GL of V. Is a group homomorphism, this thing. Remember, the composition of a homomorphism is what?
Yeah. Composition of maps.
Are we on the same table?
Let me check the chat.
It's actually, I didn't have time to put a diagram here on this, but I have a diagram for another thing, because whenever you have like composition stuff, sometimes the diagrammatic way is easier to see where things are going.
There's a question from Dimitri. Would phi go from G2 to G1?
Phi is going from G1 to G2.
I think for people doing the challenge, the drawing diagrams might be helpful.
Yeah, okay.
Learn to draw your own diagrams.
Yeah. But for the algebraic thing like George, for example, do you the composition? So you.
Yeah, I always have to remember the composition. Yes, right to left.
So have I made typo in the composition stuff? Yeah.
G1, G2,
so if I did whichever, the result will be that you should get a representation as well. Whether I did a typo in changing the order, you should get a a group homomorphism.
Yeah, if I just
the composition of a homomorphism is a homomorphism.
Right. No, it looks good to me. I don't think there's a typo.
Okay.
Yes, you're composing rho with phi. Yes, that looks good.
Yeah. Okay. So everyone on the same page? Yeah, there will be. I will be nice in the next. There's another one where involving composition as well, but for those ones,
okay.
I'll have
Dimitri.
A diagram. Yeah. Yes.
Oh, Dimitri still sees a typo that the both phi and rho start from G1.
Okay.
Let me go back to the slide. G1 to G2, and representation rho goes.
Okay, I'll come back to this just for the interest of time. We'll see whether Dimitri, he has been right before with the typo, so it will be nice for the others to catch whether this is there is a typo there as well.
G1 to G2. I'm trying to now do the diagram in my head.
Yeah, it's okay. You can ping on Discord. This is a good thing to catch before the next session.
Okay. Yeah. So yeah, Dimitri still think there's a typo, but
okay. So the question is, is everyone else on the same page as Dimitri?
I'm gonna have to get out a piece of paper.
Yeah. No, this is good. You can just maybe after this everyone can ping on the thing on Discord to see their thing. Yeah. So
okay. Yeah. Okay. I see. We're moving on to a new slide.
Yeah. So with this one, we have a diagram, so it's harder to make any typo with the diagram. Yeah. So say we have two representations, this one, V1 row 1, V2 row 2 of G, okay? We say these two representations are equivalent, okay? If there is an isomorphism from V1 to V2 such that this thing here holds, okay? So the claim is that this is the same thing as obviously this is the same thing as saying that this diagram here commutes, okay? And then if this is the case, right? These two represent equivalent. But as I said, some people, they don't use this to denote representation. They will just write this use the rows. They take it as representation. So they will write this.
Yeah, in the diagram, it looks clear to me. Let me check.
Relation.
So I guess the trick would be to take
Dimitri caught another typo?
No, that was the previous. The way to check the previous one is to just take again, I'm confused whether the upper
connection
triangle.
I don't know whether it's from my end is breaking or is it from your end. Can you say again, George?
Okay, sorry. I think the way to check the previous slide is to take the upper triangle and see if it works. But on this diagram, it looks good to me.
Okay. What about Dimitri and the rest? Bob, our friend Bob. We miss Bob. He's not able to join today.
Okay, Amir, shouldn't the upper right and left corner be GL of V1. Amir means upper right is GL of V1, lower right is GL of V2. Yeah, that's the way I see it. But Dimitri thinks this diagram looks good, so.
Okay.
I definitely find it easier to read diagrams than the words or equations.
Yeah, then the algebra, especially, yeah. Yeah, it's much more cleaner. Yeah. So that's why in the previous one, this thing here, let's make the diagram to see whether I did a typo, Dimitri was right, or that's not the case.
Yeah.
So So the second challenge is to define the thing. I think some of you can see this, but those who cannot see this, go and think about it, whether this thing defines an equivalence relation.
To be clear, an equivalence relation between the row 1 and row 2.
Yeah. I should have added that here. Thanks for doing that. I will add it on the correction on the slide.
Or actually, more precisely, an equivalence relation on all representations, right?
Yeah. On the class. Yeah. Okay. So here's two examples, nice examples that I found. So consider this group Zn, also often written like this. Remember in the thing in the early, it's like one of the groups that we work with when we first started the groups, when we were talking about cyclic groups and whatnot, long ago, I guess. Yeah. So the claim is that we can construct a two-dimensional representation of this as by defining these maps. These maps are here. Okay, so this is something that you can double check. Some of you, the eagle eyes, will notice this is a rotation. This is the group of rotations here. I hope I didn't. I think actually I didn't make any typo with the sign, but I think I probably did. There's some sign minus missing somewhere. That's my. It's actually good to ask. Can anyone see any typos here or anything? Is there any sign missing somewhere?
I think it's good. I think it's good. The top one, I think, is the transpose of what is usually seen, but it's equivalent.
Okay.
I also like that it's very explicit that it's GL of 2C.
Yeah, correct. Yeah. So, for those of you who cannot see, just try to go through this and see that this is actually this is a group homomorphism. You can even use if you cannot prove this in abstract, you see this in anything in generality for any n. Just use Z2 for instance, and try to see whether these two. First of all, they need to be a homomorphism, and second, they need to be equivalent. By going through the definition of what does it mean to be. Remember,
I'll even give a little hint. Euler is your friend.
There you go. I like that. Euler is your friend. Okay. And just I want to comment here. Remember here, obviously we are having like an abstract definition here. This is a linear map, but remember this linear map can have a matrix representation, right? You pick a basis. Let's say you pick the canonical basis of Cn, and you can then construct a matrix representation of this, and then you can have the same. You can view this as matrix multiplication. You are on both sides. That this identity here.
I think we're Right, yeah, we were looking at the next slide, sorry.
Yeah. So yeah, so this is the claim is that these two represent first of all, they are both representations, but they are equivalent representations. Okay? And now comes the notion. I hope I didn't make any typos. Again, I rely on the eagle eyes like Dimitri and so.
Bob will report back if he sees typos in the video.
Yeah. Okay.
Let's see, Dimitri. On the comments, yeah. Dimitri, Amir, to answer your question, row of, I'm having a hard time reading the chat, row of G is in GL of V, but it is a map, mapping V1 to V2. So the diagram is correct.
Yeah. Okay.
Thank you, Dimitri.
So are they talking about this diagram here?
I think they might. I think they were talking. Yes, this diagram. Yes, I think so. We're happy with this diagram.
Yeah. Okay. Okay. So, as in anywhere in any case in mathematics, when you have two structures, you want to study the things that the mappings between the structures. So this is no different than any other topics when you're studying abstract structures. So let's V1 and row 1 and V2 row 2 be representations of a group. Okay. So a linear map from the vector spaces as a linear map is a homomorphism of the two representations, not just not just any linear map, but a linear map that satisfies this. Okay, I hope I didn't make any typo again. This is the composition. So this is the equivalent to saying that this diagram also commutes. And when L is an isomorphism in the linear sense, so when these two vector spaces are isomorphic, I mean, when L defines an isomorphism, we say that the representations are isomorphic. So here's the proposition. I'm sorry, this is very small. This is one of the reasons why I was rushing to do the slides. It's like it might be a bit messy, and there might be. Can you see this?
Yeah, if I hold the screen real close, I can see it.
Yeah, you will have access to these slides anyway, so you can check also to try to correct the typos. So instead of saying another thing, this is just a convention. So when I'm using this term G linear map, what I mean is this thing. Okay. So the claim is that if this proposition here, the claim is that if you have two representations, V1 row 1, V2 row 2 of the group G, if the G linear map L is an isomorphism, then its inverse is also a G linear. So that means the inverse is also a homomorphism of representations. So in this case, the inverse is going the opposite, right? It's going from V2 to V1. So the claim is this is also, yeah, go ahead.
In the chat, Dimitri is clarifying row does map V1 to V1. Okay. Yeah, I think Amir's confusion is with the subscripts row 1 and row 2 and the vector spaces V1 and V2.
Okay. well, this one, this one is remember, this row 1 and G. This is an abstract notation that we are doing here. There's a representative, which is a linear map. This is actually a linear map from V1 to V1, right?
I've got a suggestion that might help people to think of row sub A and row sub B rather than row sub 1 and row sub 2. Then it will be clear that it's distinct from V sub 1 and V sub 2.
Yeah.
I don't know if that's helpful.
And actually, yeah, I could have made it like a little bit easier. Perhaps I should. Yeah, maybe but then that would be also a little bit confusing. Yeah, to put like maybe row and row tilde. Maybe this would make it.
Yeah, or another. Yes, it's really important to remember that these subscripts are just labels, not really numbers.
Yeah. So this is just, we are saying these like two structures, right? We have the first vector space with its corresponding homomorphism. That's what we are doing, because this is the first vector space we pick, and this is its the homomorphism, right? Yeah. And the second vector space together with its homomorphism. This is just a label, as George is saying.
But yeah, in the full square, it's easier to see how the labels correspond than in a triangle.
And where they, most importantly, where they are going. So this one is going to obviously from V1 to V1, because this is a representation, right? This row of G, this is a linear map. This is a linear map, invertible linear map, obviously, with a linear map from G1 to G1. So this is an element of GL of V1. This is GL of V1. This is a linear map of that GL of V1. Maybe I should have put belong to GL of V1, just for the thing to make it a little bit clear. But I think you can see it. Yeah.
I think it actually is good on the slides to make it as explicit as possible, because later on I just referred back to the slides, not the video, when I'm studying.
Yeah. Okay, so maybe I'll add this belongs to GL of V1, and this one belongs to GL. But these ones, this is a linear map. This is a homomorphic.
So I think now we're all on the same page. Also, Dimitri and Amir.
Okay, good. It's good to ask. Don't feel ashamed to ask a question, and thank you guys on the chat for actually helping each other out.
These questions really help clarify it for all of us.
Yeah. And I could have made a typo, the thing as well. So don't feel by no means when you have any questions, just feel free to ask, no matter what the question is. Okay, so this is homomorphism of representation. Okay, so I claim you can prove this proposition here. Now, this is a little bit, I hope I did in the sub-representations. I'm pretty sure I must have made typos somewhere else. I hope not. So, sub-representation, yeah. So, yeah. So the eagle eyes, please correct me on the thing to, yeah. So and also another thing is on the labeling, the numbering of the definitions. I hope I didn't make anything because in the last session there was misnumbering of the definitions, and yeah. So if you see that, please also let me know. So suppose this is let's V and rho be a representation of G, and W be a linear subspace. So you know what a linear subspace. So this is also a vector space of linear space and vector space is the same thing. It's just I like to use the term linear. Yeah, it's the same thing. Sometimes I use one term, the other time I use the other one. So, but they mean the same thing. Okay, so a linear subspace. Let W be a linear subspace. So we say
I'm
W.
wondering if maybe you should have the bar row parentheses G close parentheses restricted to W.
Yeah, we'll come to that actually. That's very yeah. You mean on
the
here.
definition, in the definition. Second line of the definition, I'm mentally putting in a bar row of. Okay, maybe I'm confused.
In here.
Yeah.
So this is deliberate from me. I'll clarify that. Yeah. So this is like acting on the thing, right? So you are like taking this and acting. Remember, this is these guys are this is like an action, right? So this is this guy rho of G action in the thing acting on this. So you could have, if you view it as a map as well, that's fine. Rho of G of rho of G of W belongs lies in anything in W. So if this happens, we say G is invariant. Is G invariant? Okay.
Oh,
so
okay.
We say W is G invariant. Yeah. Go ahead.
Yeah. Thank you. That clears it up for me. So that notation is the group action notation.
Yeah. Remember always, like group actions are homomorphisms. that's the thing. Is the key here. Okay. So we say W is G invariant if this is satisfied. So this is another way of saying that obviously it's G invariant under this action here of the underlying action of this. Yeah. So it's unchanged. This is the way to another way of viewing it. Okay. So W is G invariant if this is satisfied. When you act this rho of G on an element of W, it maintains. You still stay in W. You don't go outside of it. Okay. And this is for all the group elements and for every W in the linear subspace of V. Okay. Obviously, I hope you can see that the actual vector space is trivially G invariant, right? The same with the zero vector space. I'm labeling here zero V to distinguish it from a scalar. So saying this is the zero thing of the vector space, not the zero. This is the zero of the vector space. Because this group could be also abstractly, we could say it could be concretely it could be an additive group. So distinguish it. So the identity would then be zero, right? So that's why I'm writing here zero V to make it clear this is the zero of the vector space. But this is a subspace, right? It's trivial.
Yeah.
So trivially V and V and the zero space are G invariant. We are all on the same page about that, right? Okay. Looking at the definition there.
Checking the chat. I see no questions on the chat since the last round.
Yeah. Now, here's the thing. If we have a representation of G and a subspace that's G invariant subspace, okay, then we can have this. This is a representation, right? If we restrict the homomorphism rho to W, we'll see that this is a representation. In other words, this is like a homomorphism from G to GL of W. Do we agree? And this is why it's called a subrepresentation. So when we have this, we call this a subrepresentation of this representation.
Yes, thank you. Now I see the relationship between the representation and the action.
Mm-hmm.
Thank you.
Okay, no problem. Okay, so are we all on the same page? Is there anyone confused in any aspect?
I guess I was the only one confused this time. Thank you.
Yeah, no problem. Yeah. Okay, so yeah, so this is a subrepresentation. This is the definition of a subrepresentation. Okay. And now comes a very important definition, which is this notion of irreducible representation. You will see this more in the next session when we talk about unitary, unitary representation and these things. And these irreducible representations actually play a very important role in physics and other stuff, other topics. Okay, so a representation of G is said to be irreducible if the only G invariant subspaces are the vector space V itself and the zero space. That's why it's called irreducible. If that's not the case, if you can find a subspace of a non-trivial subspace of V that's the invariant subspace, then we say the representation is reducible. Okay. In the next session, we will see there are relationships between reducible and the irreducible representation in the thing. But this is why I think it was actually good that we are not covering everything, because there's a lot to unpack here. So you can go and think about. Yeah. So this is what the irreducible representations are. And now here's a proposition. I claim this is trivial to prove. Any one-dimensional representation of a group is irreducible. And you see this? Here's a hint I'm giving you. Being one-dimensional means that obviously the vector space is isomorphic to this vector space, to C, right? Or obviously we ignore the one here is C1, right? Does this C does C as a vector space admit a non-trivial subspaces?
Okay, as a vector space.
Yeah.
Yes. Yeah. Good.
It doesn't. So therefore, any one-dimensional representation of a group is irreducible. Now here's a very interesting question. You can see I was in a rush. I didn't make this in bold. Giving an n-dimensional representation of a group, is there a trick to verify, a faster way of verifying, or some easier way to verify whether the representation is irreducible? This is a very interesting question. And the answer is not generally. There are some tricks for certain use cases and certain conditions. We'll come to that in the next session. But for the time being, it's a very interesting theorem. Let's call it, as the people, it's well known. It's called the eigenvector trick. So this says, giving a two-dimensional representation, let V and rho be a two-dimensional representation of a group. Then this representation is irreducible if and only if there is no eigenvector in V common to all the P of G. Okay. So if you get the matrix representation of the G's, if you don't see any common eigenvalues amongst them, then you can conclude immediately that the representation is irreducible. There is a similar trick for 3D, but that will require things like require this G being finite. This is very interesting, right? This is, you start to see connections between different different moving. Yeah, go ahead.
I think this might be where having C complex numbers as your field becomes important.
Yeah.
I have to think about this.
Yeah. So I'll challenge you with this. I guess you can look with these these guys, these two representations. We have come across them in the previous slides. Whether these two representations are irreducible. Well, you can use this trick to see if they have the corresponding matrices has common eigenvalues. Eigenvectors. So, and another challenge 4. I hope I'm labeling the challenges correctly. Can you build a two-dimensional complex representation of the permutation group S3? I'm using here complex representation, so it's clear that we are, just to remind you that we are in sync. We are just worried about, representations with complex field. Okay, so this is it. This is the last challenge. You can see there's a lot to unpack. That's in a way it was good that, I don't know if you agree, that we haven't covered that much, because there are some other stuff that I wanted to cover. I will cover in the next session, like direct sum of representations and this type of stuff. And then we come to some important theorems about unitary representations. So first of all, obviously we'll define what a unitary representation means. We'll give some example. A famous one in quantum mechanics, for example, a concrete one that you will all recognize. But yeah, that's it. This session will be recorded. Sorry, recorded. It's already being recorded. This is